Hi, welcome to videos on Bode plot. Okay, these are the prerequisites for this video. Okay, with this initial things, so let us start with a few more Bode plots. We are asked to find what is gain margin and phase margin of this particular open loop transfer function with unity feedback. Let us find what is magnitude at origin with origin frequency as 0.1 radian per second. So that becomes 20 log 100 plus of 20 log of 0.1. This will be 40 minus of 20. This will become 20 dB. Let me write the slope table. This becomes so you have terms is 100, yes, its cutoff frequency, slope, and resultant slope. This doesn't have a cutoff frequency. Slope is plus 20. Then you have this is 1 plus 0.2s. This is a cutoff frequency of 1 over 0.2, which is 5. This will also have a slope of 20. So then this will become plus 40. Then you have this at oh sorry, before that I have this, sorry, it is 1 over 1 plus, yes, this is 1 minus 20, this will become 0, then this will become 20. Then what I have, then it is 1 over 1 plus 0.1s, which is 10 minus 20, this will again become 0. Okay. So first it is plus 20, then 0, then again plus 20, then it is 0. Fine. The initial magnitude is 20 dB. Okay, fine. So let us take the, let's write the fourth transfer function. GFS into HFS is 100 yes into 1 plus 1 plus yes by 1 plus 0.1 yes. This is omega 0.1 1 10 100 20 and initial slope is 20, sorry, magnitude is 20, and of course you have a slope of 20 dB. This will go up to 1, so let me take it as 60 dB. So it will come up to 40 dB above from the initial point. Okay, this is 40, 20, then it is 0, then this is minus 20, minus 40, minus 60. So first point is magnitude of the origin is 20 dB. The initial slope is plus 20 per decade. This is plus 20, 1 decade. This will go up to a frequency of up to 180. This is fine, and then it is 0 dB till 5. This is fine. Then it is plus 20 dB. Okay, go up by 20 dB. This is 1 decade. This will go up to 10. This will go only up to 10. Only up to 10. Then it's a slope of here as per the slope table, initially 20 dB per decade. This is plus 20 dB per decade. Then the slope becomes 0 after 1 radian per second. After 1 slope becomes 0 dB, comes it to 0 dB. And after 5, this is 5. After 5 radian per second, slope again increases to plus 20, but it is only up to 10 radian per second. After 10, it's again 0 dB per second. So it's not at all cross. This is your 0 dB line. So omega GC is not applicable. Correct. What else? What else is there? Omega PC, let us write the phase equation here. Phase equation is plus 90 degree plus of tan inverse of 0.2 omega minus of tan inverse of 0.1 omega minus of tan inverse of omega. So phase angles are, this is omega phase angle for a frequency of 0, this is plus 90. For a frequency of infinity, it is still, so this will become plus 90, okay, plus 180, okay, this will become 0 degree. So is there any point it is crossing omega minus 180? Where it is crossing minus 180 degree is not possible here. So it is, let us say it is not applicable. This omega PC is not applicable, not available for this. So neither you have omega GC nor you have omega PC. So system is never becoming minus 180 degree, and it is never having a magnitude of 0 dB. So it is absolutely stable. Absolutely stable. So this is a conclusion. Right? So let us move on to the next one. Move on to a different one. Let me take transfer function. So we take a specific transfer function having, I'm just looking for that. Okay, this is the fifth problem. Where g of s into h of s is 50 into 1 plus 0.2 s 1 plus 0.1 plus divided by square into 1 plus s 1 plus 0.02 s. Okay, let us write MAO, which is nothing but okay, 10 log, sorry, 20 log 50 minus of 2 into 20 log 0.1. This happens to be 34 plus, okay, this is, I think it is 20 log 50 minus 40 log 0.1. It is 74 dB approximately. And let me write what else? Slope table. So I have a lengthy thing. Terms, cutoff frequencies, individual slope. This is the resultant slope. So the terms are, first term is without which is not having a cutoff frequency 50 by a square. This is minus 40, minus 40. Next I have, this is the least frequency, which is 1 over 1 plus, yes, 1, minus 20, minus 60. Next it is 5, it is 1 plus 0.2, yes, it is 5, it is plus 20, this will become minus 40 now, and then this is 10, 1, sorry, it is okay, 1 plus 0.1s, which is 10, again plus 20, this will become minus 20. Then I have 1 over 1 plus 0.2s, which is 50, minus 20, minus 40. Phase equation, minus 180 degree plus of tan inverse of 0.2 omega plus tan inverse of 0.1 omega minus of tan inverse of omega minus of tan inverse of 0.02 omega. For okay, let me just take different values of omega and 5, 0 and infinity. For 0, this happens to be minus 180 degree. For infinity also it is minus 180 degree. Now let me give 0.1. Okay, let us see what is the trend. That is minus 180 plus of tan inverse of times of 0.2 alpha a plus tan inverse of 0.1 alpha a minus tan inverse of alpha a minus tan inverse of 0.02 alpha a. Calculate for 0.1. It is minus 184, and then let me calculate. It has gone down because you have a 0 also. There is a possibility that it may again become, let me just do it for maybe 5. So for 5 it is minus 192. Calculate for 10. Oh, for 10 you can see it has become minus 167.1. So in between 5 and 6, this will become minus 180. So let me find out that. Calculate for maybe 8. Maybe because 8 means it has crossed it. Maybe make it. Calculate for 7.5. I'm almost there. So let me again slightly go back. 7.5 or calculate for 7. I'm there. So calculate for 7. It is minus 180.38 degree. So what is omega PC? Omega PC is now minus 7 radian per second, meaning the phase is actually going like this. This is omega, very low value. So if it is minus 180, it is going negative, and it is slightly more than minus 180. It actually goes to more negative than minus 180, and then it again goes positive to minus 180, and then it again settles down. So this is your omega PC, where it again reaches minus 180 degree. So this is omega PC, which happens to be in this case 7 radian per second. Okay, so let us find what is the magnitude at 7 radian per second. Okay, fine. Let me get the log sheet. That is 74. Let me take it as 80, 60, 40, 20, 0, minus 20, minus 40, minus 60, 0.1, 1, 10, 100, 1K, 10K. On x-axis is omega in radian per second. On y-axis it is the magnitude of G and H in dBs. So magnitude origin is 74 dB, which is 3 divisions on the top. Then initial slope is minus 40. So this is 3 divisions down, another 3 divisions down here. And this is okay. So I'm there with minus 40 dB per decade. This will go up to 1. Okay, fine. This will go up to only 1. Afterwards, slope is minus 60 till 5. So minus 60 is actually, this is 20, this is another 20, this is another 20, this is decade. This will go up to only, this will go up to only 5. So this is till 5, that is 5, 5 is here. Okay, fine. So initially it is minus 40 dB per decade. Now it is minus 60 dB per decade. Next, what is the slope? Slope becomes minus 40 again. So this minus 40 till 10 only. So what I'll do from here, this is 10, sorry 20, this is 40, and I'll go by 1 decade. 1 decade is this 40 dB per decade, because that's your next slope. 40 dB per decade. I can join this and this till only till 10 only. So this is 10. I will stop it at 10. This is 10. So then this is now minus 40 dB per decade. Afterwards, the slope again reduces to 20. So let me come down by 20. 1 decade. This will be the slope from 10 to 50. So this is the slope till 50 dB. So 50 is here. Okay. This is now minus 20 dB per decade. And later slope is minus 40. So unfortunately, I don't have 40 dBs of this. Instead of going 40 dB down, you can go by 12 dB. So if it is 40 dB down, you have to go by 1 decade on x-axis. Now you go by only 12 dB down, go by 1 octave. So 1 decade is the ratio of the frequency f1 f2. Okay, f2 by f1 should be 10. Here f2 by f1 should be 2. There should be a ratio of 2. That means uh, the last one is 50 here. After 50, come down by hardly 12 dBs. So where is 12? So this is 2, 4, 6, 8, 10, 12. This is 12. Go by 1 octave. Octave means twice of 50 is 100. I'm here. So this is now minus 12 dB per octave or minus 40 dB per decade. So this is minus 40 dB per decade, which we got it by minus 12 dB per octave. So that's what. Okay, let me write the transfer function for this. The fifth transfer function is GFS into HFS is 50 into 1.2 yes by 1 plus 0.1 yes by a square plus 1 plus yes plus 0.02 yes. So I was referring to this. So 20 plus or minus 20 dB per decade is equal to plus or minus 6 dB per octave. It is not simply 20. This is applicable for any multiples of 20. So that will be multiples of 6. If it is 40 dB per decade, then it is 12 dB per octave. If it is 80 dB per decade, then it is 80 will be 4 times. So what is 4 times of 6? It is 24 dB per decade. Oh, sorry, octave. Okay, we are done with the plot now. So once we are done with the plot, let us find out what is omega GC. Omega GC comes out to be this. Omega GC is, if you find out, this is 1 2 3 3 3 3, this is 3 here, this may be around 3.7 radian per second. So at the 3.7, at omega GC, which is 3.7, let me find out what is the phase. This is my phase equation. So at 3.7, so what is the phase? It is minus 202 degrees, correct? And at omega PC 7, at 7 how much you have? At 7, this is 5 6 7, this is 7. So at 7 I have this. So this is my magnitude. So the magnitude is almost so magnitude at omega PC is, this is 10, almost minus 12 dB, minus 12 dB. So what is gain margin now? Let us try to find out what is gain margin, phase margin. Let us summarize. Omega GC is 3.7 radian per second. At that point, phase at omega GC is minus 202 degrees. Omega PC is, that's what we found. So omega PC is 7 radian per second. The magnitude at omega PC is minus 12 dB. Therefore, gain margin is minus of minus 12, which is 12 dB, whereas phase margin is 180 degree plus phase at omega GC, which is 180 degree plus minus 202. So this happens to be 20, minus 22 degree. So you have a GM of plus 12 dB, you have a PM of minus 22 degree. So this is a peculiar case where you have GM positive and PM negative, or the phase margin negative. Whenever you have the phase margin negative, that is the one which decides the stability of the system. Now, what does this gain margin 12 dB means? The existing gain, which is now 50 here, 50, if it is multiplied by 10 to the power of 12 by 20, then the system is oscillated. So this whatever value you will get. So this is the existing gain 50. What is this? This is 12 dB, can be written as 10 to the power of 12 by 20 in the actual value. So it is, how much is that? 10 to the power of 12 by 20 is 3.98. It is 3.98. So if the gain becomes 15 to 3.98, how much is that? It is 199. When the gain becomes 199, then poles come onto the imagined axis. Poles come onto the imagined axis. So now here, of course, we say system is oscillatory. When when your PM is negative, it's meaning that poles are on right hand side of the S plane. So system is unstable. So whenever this is negative, in spite of this being positive, the system is unstable. So here the system is unstable because PM is negative in spite of having gain margin positive. Correct? So I'll just give you an exercise to the same problem. You make this equal to, maybe, of course, you can try out in MATLAB. So make this equal to 500. The moment you make this equal to 500, this value will become very high. So change the scale, make this equal to 500. You can surprisingly see GM will be uh, positive, GM will be positive, and Okay, sorry. GM will be negative, GM will be negative, and PM will be positive. So this is what you're going to get if you make this 500. Meaning gain margin will become negative, phase margin is positive, then system will be stable. Then system is stable for 500. I'll just give you a task to carry out this. Replace 50 by 500 and redo it, and you change the scale. Every inch you take it as 40 dB so that you can comfortably plot the graph. Then your GM will be negative, gain margin, phase margin is positive, system will be stable. Okay, we'll see few more graphs in the next video.